If you've been around me lately, maybe you've heard me talk about my body battery. Two things you should know about me: I love data, and I'm a masochist. I've been traveling much more than usual lately, all for good reason. But on top of that, I have lectures to teach, papers to grade, papers to write, strategy to develop, and nothing short of an addiction to exercise that is apparently unquelled by the Florida summer heat and humidity. Somewhere in there, there's a book I'm trying to write too. Oh, and sometimes I get to do this podcast. It's mentally and physically exhausting. Even so, I know that I need to monitor my own health, and since I love data, I use a Garmin watch. I know what you're thinking, but no, this podcast is still not ad supported. I just love data, and my Garmin watch gives me data. One of those data points is body battery. According to what Garmin says, body battery is calculated by analyzing signals from your heart, like heart rate variability or HRV, and stress, as well as sleep quality and activity. Because of all my various activities, I have often been asked if I ever sleep. I do, actually. I place more value on sleep than almost anything else, and I aim to get the best night's rest I can. It doesn't always work, though, and especially when I'm traveling for a big conference, it's not uncommon for me to wake up with a body battery of 29%, draining to around 5% before noon, and I basically become a living zombie. But one night, while traveling a few weeks ago, I achieved the absolute holy grail of the health tracking world. I managed to get 8.5 hours of uninterrupted sleep. When my alarm went off, I looked down at my Garmin watch and there it was, a body battery score of 100%. I almost didn't believe it. This virtually never happens for me, even when it is my explicit goal. I felt like a structural masterpiece of human biology. But right before I had closed my eyes the night before, I made the classic mistake of doing a final scroll through social media, and I stumbled across a Facebook meme that read, "Poor sleep habits trigger the brain to eat itself, science finds." So I was lying there, my Garmin was trying to optimize my recovery, and my digital feed was telling me that my gray matter conducts acts of cannibalism when I stay up late. Naturally, I couldn't just ignore that. There was no link in the meme, of course, because why would an internet graphic ever provide a primary source? So, I had to do my own digging. What I found is a classic case of internet sensationalism colliding with some incredibly alarming, legitimate science. It's an all-new Prove It To Me. Welcome back to Prove It To Me. I'm your host, Dr. Matt Law. Today we are taking a hard look at sleep, or more accurately, what happens to your neurological infrastructure when you don't get it. We are going to take our time building this episode out step by step. I want to make sure that we get the complete picture of the data, because sleep deprivation is one of those occupational and lifestyle hazards that we all love to brag about surviving, right up until the check comes due. To kick things off, I pulled an excellent overview article from an organization called Daybreak that perfectly synthesizes the overall landscape of this brain eating itself phenomenon. They had their content clinically reviewed by an ENT and sleep specialist, so it handles the concepts with a great level of professional respect. Let's clear the air on the headline first. No, your brain is not literally opening up a mouth and chewing on its own neurons when you pull an all-nighter. But what is happening is that your brain's cellular housekeeping system gets aggressively thrown out of equilibrium. When you get your solid 8 hours, your brain activates something called the glymphatic system. An NIH paper titled The Neuroprotective Aspects of Sleep breaks this down beautifully. Think of this as the nightly deep clean or the third shift janitorial crew for your skull. While you are unconscious, this glymphatic plumbing system flushes out cellular waste, toxins, and metabolic byproducts, specifically harmful proteins like beta amyloid and tau, which are heavily linked to neurodegenerative conditions like Alzheimer's. The brain is incredibly metabolically active during sleep. The glymphatic system actually increases the interstitial space in your brain by roughly 60% while you sleep, allowing the cerebrospinal fluid to rush in and effectively clear out the toxic cellular trash. The NIH paper put it perfectly. The brain functions as a one-way street. It cannot process complex sensory information and clear massive amounts of cellular waste at the exact same time. When you chronically skimp on sleep, that janitorial crew doesn't show up for work, or they get sent home early. The toxic waste builds up in the cells, and that is where the trouble begins. So, where did this horrifying internet concept of the brain eating itself actually originate? It wasn't completely made up. It traces back to a real study published in the Journal of Neuroscience back in 2017, led by a team out of the University of Wisconsin-Madison, alongside researchers in Italy. The team wanted to see what happens to the support cells in the brain when rest is withheld. So they looked at the brains of chronically sleep-deprived mice. They focused on two specific types of cells: astrocytes and microglia. Astrocytes are like the structural caretakers of the brain. They trim down worn-out synaptic connections, basically pruning the bushes of your neural pathways to keep things neat. Microglia are the specialized immune cells, the security guards that hunt down damaged cells and cellular debris. The methodology here is a wild ride. They used 4-week-old mice and put them into 4 distinct behavioral categories. First, the sleeping group, left completely alone during their normal sleep cycle. Second, the spontaneously awake group, analyzed during their natural nighttime active phase. Third, the acutely sleep-deprived group. These mice were kept awake for 8 hours during their normal sleep cycle. How do you keep a mouse awake for 8 hours? The researchers introduced novel objects into the cage and tapped on the side of the enclosure whenever a mouse started looking drowsy. Finally, the chronically sleep-restricted group. These mice were subjected to 4.5 days of severe sleep restriction, knocking their overall sleep duration down by 70%. At night, they were placed on a slowly rotating platform positioned just 2 to 3 centimeters above a tray of water. If the mouse stopped walking or tried to curl up for a nap, it slid down into the water, got wet, and had to walk over to a heat lamp to dry off before jumping back on the treadmill. It is an incredibly effective, if slightly brutal, way to stimulate the relentless grind of chronic sleep debt. Once the experiment wrapped, the researchers used an advanced neuroimaging tool to build 3D volume reconstructions of the synapses in the frontal cortex. In the healthy sleeping mice, about 5.7% of the synapses showed signs of astrocytic phagocytosis, meaning the astrocytes were doing their normal baseline trimming of cellular components. In the spontaneously awake mice, it was 7.3%. But in the acutely sleep-deprived mice, that number jumped to 8.4%. And in the chronically sleep-restricted mice, the treadmill over water survivors, astrocytic pruning surged to 13.5% of all synapses. The astrocytes were actively engulfing parts of the synapses at more than double the rate seen in a resting brain. Here is the kicker that directly disproves a common assumption. You might think these support cells were just cleaning up weak, failing synapses. But the researchers tracked the axon-spine interface size, a direct metric for synaptic strength. They discovered that the astrocytes were preferentially targeting the largest and strongest synapses. Because these synapses had been fired continuously during extended wakefulness, they suffered from intense metabolic strain. The astrocytes were overclearing the brain's heavily used critical infrastructure. But the real red flag belongs to the microglia. Acute sleep loss didn't really activate them, but chronic sleep loss completely set them off. Under chronic sleep restriction, the microglia changed morphology, shifted into an active immune state, and began aggressively eating presynaptic terminals. They did this without showing any overt signs of neuroinflammation in the cerebrospinal fluid. The microglia were primed, sitting in a hypersensitive, sustained state of activation. The authors warned that when microglia are primed like this, it can lead to abnormal, wildly exaggerated responses to any secondary insult down the road, increasing the brain's baseline susceptibility to neurodegeneration and long-term cognitive damage. So, when the internet says your brain eats itself, what they are clumsily trying to describe is that the chronic sleep deprivation causes your brain's defense mechanism to turn on itself, stripping away essential neural hardware because it can no longer tell the difference between trash and baseline infrastructure. But as safety professionals and critical thinkers, we always ask the next logical question. Mice are great, but what about people? The Daybreak summary points to a massive warning sign, highlighting that human data is starting to show the exact same structural echoes. They noted a 2020 study published in the journal Neurology showing that just one single night without sleep can raise tau protein levels, which is a key Alzheimer's risk marker. I pulled that paper. It is titled Effects of Acute Sleep Loss on Diurnal Plasma Dynamics of CNS Health Biomarkers in Young Men. The research team wanted to know if skipping a single night of sleep would alter the blood levels of specific biomarkers associated with Alzheimer's disease. They recruited 15 healthy young men, with an average age of about 22 years old, with normal body mass indexes, no chronic medications, and self-reported good sleep quality. They put these guys through a two-condition crossover study in a laboratory. In the first condition, they were allowed a normal night of sleep in a pitch-black room from 10:30 p.m. to 7 a.m. In the second condition, they were subjected to acute overnight sleep loss. To keep them awake, the researchers kept the lights on at 250 lux, restricting them to their beds in a semi-recumbent position, and allowed them to play board games, watch movies, and talk under direct supervision. Compared to the mice, playing board games in bed sounds like a luxury retreat, but the physiological results were anything but relaxing. The researchers drew fasting blood samples in the evening before the intervention and the morning right after. They were specifically looking for beta amyloid and total tau, or t-tau. Alzheimer's disease is hallmarked by the pathological accumulation of extracellular beta amyloid in plaques and intracellular tau proteins in neurofibrillary tangles. What happened after one night of staying up playing board games? The evening to morning ratio for total tau in the blood spiked by 17.2% after the night of sleep loss. After a normal night of sleep, the t-tau levels only increased by 1.8%. That is a statistically significant surge of a neurodegenerative biomarker leaking into the peripheral blood after just one missed night of sleep. Interestingly, they did not see significant changes between the sleep conditions for the beta amyloid markers or for other neuroaxonal damage markers like neurofilament light chain, NFL, or glial fibrillary acidic protein, GFAP. The levels of GFAP and one of the beta amyloids actually decreased overnight regardless of whether the guys slept or not, proving some biomarkers just have their own diurnal sleep-independent rhythms. But that total tau spike is the smoking gun for acute sleep deprivation. The researchers noted that increased T tau levels in the blood might indicate sustained high neuronal activity during prolonged wakefulness, or it could potentially indicate increased neuronal damage that results in the tau leaking into the interstitial fluid and subsequently into the blood. Let's pause and acknowledge that that was a lot of crazy, complex words, and I apologize for that, but this is important. Let's frame this for occupational safety and health. We're not talking about 70-year-old retirees. We're talking about healthy, fit 22-year-old men. One single all nighter, the exact type of schedules we routinely force upon our shift workers, our turnaround maintenance crews, and our emergency responders was enough to significantly alter the plasma dynamics of a key pathogenic biomarker for Alzheimer's disease. When we ask an employee to work a 24-hour emergency shift, we are actively manipulating the chemical environment of their central nervous system. Now, if acute sleep loss is bad, what does chronic low-level sleep deprivation do over the course of decades? The Daybreak summary highlighted a massive 25-year study that found sleeping fewer than 6 hours per night in midlife was linked to a 30% higher risk of dementia. I remember this study vividly when it came out. Long before we had kids or dogs, my wife always functioned on less sleep than me. I was the guy fiercely guarding my 8 hours, and this study was my ultimate I told you so moment. The paper is titled Association of Sleep Duration in Middle and Old Age with Incidence of Dementia, published in Nature Communications in 2021. This research team used data from the Whitehall 2 cohort study, which tracked nearly 8,000 British civil servants over a massive 25-year follow-up period. Most dementias are characterized by pathophysiological changes that occur over 20 years or more before clinical diagnosis. If you only study people for 5 years before they get diagnosed, you run into reverse causation bias. Did the poor sleep cause the dementia, or was the undiagnosed early stage dementia causing the poor sleep? To filter that out, the researchers specifically looked at sleep duration when the participants were 50, 60, and 70 years old. They categorized normal sleep as 7 hours a night and short sleep as 6 hours or less. The results were incredibly consistent. Short sleep duration at age 50 was associated with a 22% increased hazard ratio for incident dementia. Short sleep at age 60 was associated with a 37% increased risk. But the most alarming finding came from looking at the trajectories of sleep over time. They tracked the participants who maintained a persistent short sleep duration, meaning they consistently slept 6 hours or less at age 50, 60, and 70. Those individuals had a 30% increased risk of dementia compared to those who persistently got normal sleep. This association remained rock solid even after the researchers statistically adjusted for socio-demographic factors, behavioral choices, cardiometabolic health, and mental health factors. Even when restricted only to participants with no history of mental disorders before age 65, the 30% increased risk remained. The researchers hypothesized the mechanisms here likely involved exactly what we saw in the mice and the young men: impaired clearance of amyloid beta from the brain, potentially due to impaired glymphatic function, leading to neuroinflammation and atherosclerosis. This is the ultimate warning. We tend to view sleep deprivation as a temporary hazard. You're tired today, you'll sleep in on Saturday, and everything resets. This 25-year study proves that the neurological bill doesn't just disappear. If your workforce is constantly running on 6 hours of sleep or less because of shift design, long commutes, or burnout, they are not just increasing their risk of a struck-by incident today. They are fundamentally increasing their risk of severe cognitive decline in their retirement years. Now, Let's talk about the physical mechanics of how we sleep, because it's not just about the hours on the clock. It's about the quality of the biological processes happening while you are unconscious. Both the Daybreak article and the NIH paper highlight a critical point. The brain's glymphatic system requires a highly specific oxygen rich environment to function. But what happens when the oxygen supply is cut off? If a worker suffers from obstructive sleep apnea, or OSA, a condition where the airway repeatedly collapses during sleep, their brain is subjected to intermittent hypoxia, meaning it is repeatedly starved of oxygen. When your oxygen levels drop, your brain registers it as a physiological crisis. It forces a microarousal, a tiny, often unremembered moment of wakefulness, just to jumpstart your breathing again. If this happens dozens or hundreds of times a night, two things occur. Number one, the glymphatic system fails. You never spend enough sustained, uninterrupted time in the deep N3 delta wave sleep, or the REM cycle, for the cerebrospinal fluid to properly flush out of the beta amyloid metabolites. Number two, systemic inflammation. The repeated oxygen deprivation places the brain under massive oxidative stress, triggering neuroinflammation and cell damage. This is the ultimate insidious hazard. A worker might be in bed for 8 hours, but if they have untreated sleep apnea, their brain is still accumulating Alzheimer's biomarkers and their astrocytes are still overpruning their synapses. They are sleep deprived while appearing fully asleep. As the Daybreak article points out, many people don't realize their brain is being affected until the daytime symptoms appear: crushing fatigue, poor memory, lack of focus, or their partner telling them they choke and gasp in their sleep. So, we've covered a lot of terrifying neurology today, but the good news is that the brain is incredibly plastic. The Daybreak article explicitly notes that if you catch these issues early, before long-term structural damage sets in, the effects are largely reversible. When you finally provide the brain with the rest, oxygen, and blood flow it needs, it will start repairing and resetting. So, what are the actionable takeaways for you, your workforce, and your own gray matter? Number one, treat sleep as critical infrastructure. The NIH paper established that the brain functions as a one-way street. It cannot process complex sensory information and clear cellular waste simultaneously. Sleep is not a luxury. It is a non-negotiable biological maintenance window. Stop glorifying the grind of functioning on 4 hours of sleep. If you are an EHS professional doing that, you are actively degrading your own executive function and decision-making capabilities. Aim for 7 to 9 hours consistently. Number two, screen for apnea. If you wake up exhausted after 8 hours, if you snore heavily, or if you find yourself getting up multiple times a night, you need to get screened. You don't necessarily have to go to an expensive in-person sleep lab anymore. At-home sleep tests are highly effective for diagnosing clinical sleep apnea. If you have it, treat it. Whether it's a CPAP machine or an FDA-cleared mandibular advancement device that keeps your airway open, get the oxygen flowing back into your brain. Number three, manage the environment. If you manage shift workers, understand that you are fighting human biology. You need to build schedules that allow for true, restorative sleep cycles. Furthermore, educate your workforce on sleep hygiene, cutting caffeine after 2 p.m., reducing screen time, and maintaining consistent sleep and wake times. Now that's going to wrap it up for this episode. We went deep into neurology today, and like I said, we had some pretty complex words in there. Hopefully you stuck with me and didn't fall asleep. But it is critical to understand the actual mechanisms of fatigue, not just the symptoms. Your brain is not literally eating itself, but if you don't let it sleep, it will absolutely start taking the furniture apart. I'll link all the studies, including the Daybreak summary, the mouse data, the Alzheimer's biomarker study, and the 25-year Whitehall 2 cohort in the show notes so you can read them for yourself. If you got something out of today's conversation, please take a second to rate and review the podcast on Apple Podcasts or Spotify. It truly is the best way to help other safety professionals find the show. If you have a topic you want me to tackle, shoot me an email at contact@proveitpod.com. For now, stay safe, protect your airway, and get some sleep. And I'll catch you on the next one. Prove It To Me is produced by me, Matt Law. Original music by Wes London. You can find this podcast on Podbean, Apple Podcasts, Spotify, YouTube, Amazon Music, and iHeartRadio. Like what you've heard so far? Please like, subscribe, and follow wherever you get your podcasts, and leave a 5-star review on Apple Podcasts. Got questions about what we talked about or research that you want to share? Send an email to contact@proveitpod.com. The views and opinions expressed in this podcast are those of the host and its guests and do not necessarily represent the official position, opinion, or strategies of their employers or companies. Examples of research and data analysis discussed within this podcast are only examples. They should not be utilized in the real world as the only solution available, as they are based on very limited, often single use case, and sometimes dated information. Assumptions made within this discussion about research and data analyses are not necessarily representative of the position of the host, the guests, or their employers or companies. No part of this podcast may be reproduced, stored in a retrieval system, or transmitted in any form or by any means, mechanical, electronic, recording, or otherwise, without prior written permission of the creator of the podcast. The presentation of the content by the guests does not necessarily constitute an active endorsement of the content by the host.